A hash table is a data structure that implements the basic operations of inserting elements, looking up if an element is present, and deleting elements. These are exactly the operations that we saw are needed to solve the contains duplicate problem. So let's go back to that problem and see how it helps us motivate coming up with the design of a hash table. To refresh your memory, in the contains duplicate problem, we are given a vector of integers, and the problem is to determine if any integer appears more than once in this vector. We can solve this problem using any data structure that implements the operations of insert and contains. We make a pass over the vector, and for each entry, check if the data structure already contains the element. If it does, then we know there is a duplicate, and we can go ahead and return true. If it doesn't, then we can insert the element into the data structure. If we make it through this pass over the entire vector without returning true, then we know that there is no duplicate. So a hash table is tailor-made to solve this problem. A hash table implements what we might call the dictionary abstract data type. In this basic version of a dictionary, we can insert elements, check if an element is already in the dictionary, and erase elements. You could imagine more elaborate versions of the dictionary abstract data type where besides contains, you might also like to have an operation like find, where that retrieves an element, say by returning a pointer or an iterator to it. But to keep things simple for this video, we're just going to stick to contains, which just returns a Boolean, whether an element is present or not. On the specification for the Leet Code version of contains duplicate, it says that the input vector has a maximum size of 100,000, and the numbers in the vector are promised to be between -1 billion and +1 billion, integers in that range. To keep things simple here, I'm going to assume that all the entries of the vector are non-negative. So let's assume that they are at least 0 and strictly less than 1 billion. So the first idea is that since the entries of the input are non-negative, we can actually use them as indices into a vector. So we're just going to create a vector of 1 billion booleans called present, and we're going to initialize this vector to all false. And now we're just going to make one pass through the vector, and for each x that we come across, we're going to check if present of x is true. So that would mean that we've already seen x. If yes, then we can return true. If not, then we mark x as present and continue. So Leet Code does not accept this solution. This exceeds the running time. So do you see what the problem is? What's the bottleneck in this solution? Well, of course, the problem is that we have to initialize this vector of size 1 billion to all false at the beginning of the algorithm. And this time dwarfs the time it takes to iterate through the vector because the vector only has size 100,000. So that seems pretty wasteful, right? We initialize this huge vector of 1 billion elements when we're not going to touch most of the entries of that vector. Right? Since the input has size at most 100,000, we're going to touch at most 100,000 entries of the vector. I mean, mark as true at most 100,000 entries of the vector. Okay, so it seems wasteful to initialize a vector of size 1 billion when we're only need to remember 100,000 things. So let's see if we can somehow get by using a smaller vector to store the entries that we've seen. And we're going to do this at first at the expense of sometimes having a wrong answer. Okay, so let's set a budget. Let's say that we only have the time and space to initialize a vector of size 1 million instead of 1 billion. So 1 million, this is still 10 times larger than the size of the input vector. Now, since the numbers that we're going to see are between 0 and 1 billion, we need some way to map these numbers into valid indices into our vector, which now only has size 1 million. So let's define a variable size to be 1 million. That is the size of the vector that we're going to store. So one way that we can map these numbers between 0 and 1 billion into a number between 0 and strictly less than 1 million is to look at the remainder when x is divided by 1 million. So when x is non-negative, this is always going to be a non-negative integer, and it's going to be between 0 and 999,999. So thus, it will be a valid index into our vector. So now let's try this code out. We set size to be a number close to 1 million. So here I've used 999,863. And then the algorithm is exactly the same as before, except that now to get a valid index into the vector, we first take the entry in the input vector nums and we take it modulo size. And once we do that, then we get a number between 0 and size minus 1, so it's a valid index into our present vector. And actually, surprisingly, this code passes all of the Leet Code tests. So I've simplified the code somewhat for the slide here. You can see the Godbolt link for the actual code that passes the Leet Code tests. But of course, this algorithm can have wrong answers. It can say that there's a duplicate when there actually is not. How can that happen? Well, if there's two distinct integers with the same value modulo size, then this algorithm would report a collision when there's really not one. So that's why I chose this kind of funny value of size, 999,863, rather than simply 1 million. So if we took 1 million as size, then the algorithm would report a duplicate whenever the input contained two elements that are both a multiple of 1 million. And it seemed like that would be a more likely thing for a human to do in coming up with a test case than having, say, two things that are both a multiple of 999,863. Indeed, if you try this code with size being 1 million, it's not going to pass all the tests on Leet Code. Okay, so let's look at this approach a bit more generally. We can think of this approach as having buckets, and these buckets are labeled by integers 0 through size minus 1. Now, when we see an input x, we decide what bucket to put it in by taking its modulus with size, and that's going to give us a number between 0 and size minus 1. So we have this mapping which goes from a non-negative integer to the label of one of the buckets, and such a mapping is called a hash function. So for example, if we have 5 times size plus 1, when we take that modulo size, we just get 1, so that input goes into bucket 1. Now, if we also had input 1, well, that's also equal to 1 modulo size, so that would also be mapped to bucket number 1. And when we have two distinct integers being mapped to the same bucket by the hash function, this is called a collision. So collisions are bad in a hash table, and we want to limit them as much as possible. So another question you might have at this point is, where did this modulus function come from? Well, it has several properties that make it a good example of a hash function. So first, any hash function, it needs to map the data to the labels of the buckets. And the labels of the buckets are array indices. So they're going to be, integers of the form from 0 to like size minus 1. So the modulus function, it very naturally does this, right? Because if we just take a number modulo size, a non-negative number modulo size, we're going to get a number, an output between 0 and size minus 1. So that's one nice property of this modulo function. Another key property of a hash function is that it should distribute the inputs evenly over the buckets. So of course, this is not always going to be possible. But suppose for a second that we just randomly choose an integer between 5 times size and 6 times size minus 1. Now, each of these numbers hashes to a different bucket under this modulo hash function. Right? 5 times size will be mapped to bucket 0, 5 times size plus 1 will be mapped to bucket 1, etc. So thus, if we randomly choose a number in this interval from 5 times size to 6 times size minus 1, every bucket is equally likely to get it. And now note that this holds not just for this interval that I've illustrated here, but for any contiguous interval of length size. So what that means is that if we randomly choose a non-negative integer x and look at the result modulo size, each bucket has the same chance of receiving it. And this is a very good property for a hash function to have. This is going to reduce the chance of collisions amongst the inputs. Finally, we want the hash function to be fast to compute. Ultimately, we want the hash function to be able to compute the hash function in constant time. So the modulus function satisfies this as well. Okay, so now we have a trade-off. We don't want too many collisions, but we also don't want to use too much memory. So typically we take the number of buckets to be a constant factor times the number of numbers that we want to store. So for example, if we want to store n numbers, we could use 2n buckets. So this ratio of the number of elements you want to store to the number of buckets is a key property of a hash table, and it's called the load factor. So in this example, if we are storing n elements and we use 2n buckets, then the load factor is 1/2. With a load factor like this, it's going to be inevitable to have collisions. So we need to develop some method to deal with collisions. To handle collisions, we can simply store all the elements that reach a given bucket. So each bucket can have its own data structure, say a deck, to store the elements that reach that bucket. To insert an element into the hash table, we first use the hash function to compute which bucket it should be in, and then we add it to the front of the deck stored at that bucket. So here's an illustration of that in action. Say that we want to insert the element size plus 1 into our hash table. So first we compute the modulus of size plus 1 with size. That's equal to 1, so we see that size plus 1 should go into bucket 1. Then we add size plus 1 to the front of the previously empty deck stored at bucket 1. Next, say we want to insert 5 times size minus 1 into the hash table. So we compute its modulus with size, and we get size minus 1, so we see that it should go into bucket size minus 1. Then we add it to the front of the previously empty deck stored at bucket size minus 1. Next, say that we want to insert 10 times size plus 1 into our hash table. So we compute its modulus with size, we get the answer 1, so we see that it should go into bucket 1. And then we add it to the front of the deck stored at bucket 1. So we see that this is how we can insert items into our hash table and handle collisions. So stepping back a little bit, there are two basic components to a hash table. Well, we have some underlying array where we're storing the data. And we need a hash function to map the data we want to store to an array index. That's the first component of a hash table, this hash function. Then we also need some mechanism to handle collisions. So the method that we have discussed here, where each bucket has its own data structure to hold the elements hashed to that bucket, is called separate chaining. So let's try out our little homemade hash table on the contains duplicate problem. So here we're going to use a vector of size twice the number of integers that we want to store. So this is going to give us a load factor of 1/2 after all the elements of the input nums are inserted into our hash table. Each bucket holds a dec, so our underlying data structure is a vector of size many decs. Now, given an x, we determine which bucket it should go into with the modulus function. And here's the most interesting part of the algorithm. So this is like the contains function. We know that now we know what bucket x goes into. So to see if the data structure already contains x, we need to search through this deck, the deck in this bucket, to see if x is there. And this is just a linear search. So we potentially have to look through all the items in the deck. So this is why, to keep the running time down, it's very important not to have too many items in any one bucket. If x is in the bucket, then we return true. Otherwise, we add x to the front of the deck at this bucket. And finally, as usual, if we pass through the whole vector without finding any duplicates, then we return false. So let's look at this contains function of our homemade hash table. We want to see if the hash table contains x. So the first step is to compute the hash of x, for example, x modulo size, to see which bucket it should go in. When the hash function can be computed in constant time, then this step is constant time. And now once we know the bucket that x goes in, we can do a linear search through the deck stored at this bucket to look for x. So this is going to take time proportional to the number of elements in the bucket. So that's the worst case complexity of the contains function is proportional to the maximum number of elements stored in any one bucket. This is why we want a hash function to evenly distribute the elements across the buckets. But you can see that no matter what hash function we choose, we can always adversarially pick a sequence of inputs which all map to the same bucket under that hash function. So then our hash function just degrades to whatever data structure we are using at each bucket. So in our case, we're using a deck, so contains can take worst case time theta of n. In the worst case, every item is mapped to the same bucket, and thus to look for an item, we just have to search through the entire deck at that bucket, which can take time theta of n. So to argue that a hash table has good performance, we have to make some assumptions about the inputs. So a common assumption that is made in the analysis of hash tables is what's called the simple uniform hashing assumption. Under this assumption, any given element we encounter is equally likely to hash to any of the buckets. So we get this assumption, for example, when the elements are chosen to be random non-negative integers and we use modular hashing. So let's look at a single bucket under the simple uniform hashing assumption. Each element inserted into the hash table has probability 1 over the number of buckets, which we're calling size. So 1 over size probability to end up in this bucket. So after inserting n elements, the expected number of elements in this bucket is n divided by size. Typically, we're going to choose size to be something like 2 times n to achieve a constant load factor. So when you do this, then you can show that the average time taken by the contains function under this simple uniform hashing assumption is constant. Now let's look at the running time of insertion. There are a couple of considerations here about the design of the hash table. So in our discussion, we have focused on fixed size hash tables. In this contains duplicate problem, we knew how many elements we wanted to store in advance. But you might also want to consider a dynamic hash table that you can continuously add elements to, like in a resizable array. So you can do this with techniques similar to those used in a resizable array. When the load factor exceeds a threshold, then you can just allocate a new array of double the size and then rehash all the elements into these new buckets. So on an insertion where this happens, we spend time proportional to the number of elements stored in the hash table. But just like in a resizable array, this operation does not occur very frequently, so we can still get constant amortized time for insertion. Another consideration is if we want to check if an element is already in the hash table before insertion. So we might do this if we don't want to store duplicate keys, or if we want to keep records with the same key stored together. So in this case, we have to do a contains operation before the insertion, so we can only hope for average case constant running time, because that's what we need for contains. If we have a fixed size hash table and do not search before insertion, then insertion in a hash table can just be done in constant time. So in that case, we just have to compute the hash of the input and do a push front on a deck, and we can do both of those in worst case constant time. Finally, let's do contains duplicate again using a hash table in the standard library. For this application, we can use standard unordered set. So this data structure maintains a collection of unique keys. So before inserting a key, it checks if the key is already present in the hash table. And if it is, then nothing is done. If it's not, then the key is inserted. So standard unordered set is also dynamically resized. So we can start with just an empty hash table, like we're doing in the first line of the algorithm here. So then, as usual, we iterate over the vector and check if each element is already in the hash table with the contains function. If it is, then we can return true. And otherwise, we add the element to the hash table with the insert function. If we finish the for loop without finding any duplicates, then we can return false. So hash tables in C++ are essentially required by the standard to be implemented using a separate chaining approach, where the elements are stored in buckets. So there are even member functions that give you access to information about the number of buckets and the number of elements in each bucket. So you can see these member functions here. I've taken this from CPP reference. Under the simple uniform hashing assumption, the average case running time of contains and erase is constant, and insert takes amortized average case constant time because the hash table is dynamically resized. So some insertions might take a long time if that insertion causes the hash table to exceed the threshold of the load factor, so then it has to allocate a new array of double the size and rehash all the elements into the new array. So because standard unordered set maintains a collection of unique keys, it has to do a search operation before insertion. So all of insert, contains, and erase have worst case running time theta of n. And again, the worst case is where all n elements just end up being hashed into the same bucket.